have a look at this case where liquid and solid are regular solutions. So we looked at the homogeneous construction, right? And we also looked at homogeneous construction basically gives you the chemical equilibrium conditions at a given temperature, right? This is done at a given temperature. Remember, here some T is specified. T is specified. When we are drawing the free energy composition diagram, we already know the T. So T is specified, and you have alpha and beta, and you can see that it is not really the common tangent basically tells you a condition where mu A alpha equals to mu A beta and mu A alpha equals to mu beta, and at the where the common tangent, so the points touches the curves, the points it touches the curves. If I look at that point, so this point for example, or this point for example, basically gives me the equilibrium compositions of the alpha and beta phases that are in equilibrium, like alpha and beta are in equilibrium. So XB alpha equilibrium is the composition of the alpha phase that is in equilibrium with the beta phase. Similarly, XB beta equilibrium, this composition is basically the composition that is of beta phase that is in equilibrium with the alpha phase, right? So basically, it gives you a solution, a graphical solution of these equations, right? Of these equations, it gives you a direct graphical solution, right? We can look at more complex diagrams also to look at and estimate the graphical solutions. For example, here liquid and solid. So if you look at that liquid and solid, there are two phases, liquid and solid. But you can see this diagram is quite complex because you have L plus S here, E plus L plus S here, and there is only one point where it changes, right? It's continuous, one point where it changes. Basically, L plus S are regular solutions. So this is where you have the pure liquid, and then you have solid. Now, if you look at that, at temperature T3, you have one composition E, then F. F is the composition of the solid phase in equilibrium with the liquid. So F is the composition of the liquid phase, right? This is the liquidus, right? This is a liquidus line. This is liquidus. So basically, if I tell what are the liquidus lines, so basically I can easily tell what are the liquidus lines. So this is liquidus, and similarly this is also liquidus, right? So this is also liquidus, right? This is the liquidus line. These two are the liquidus lines, and similarly this is your solidus line, right? Solidus basically is separate. So basically you have if you look at that, you have this solidus line here, and this is also solidus. Okay. Right, so right, you have this solidus line, right? So you have, so now if you look at the compositions, F and G represent. So if you look at F and G, I'm going the other way. So F and G represent the equilibrium compositions of the liquid phase that are in equilibrium with the solid phase. So F, for example, is the composition of the liquid phase that is in equilibrium with the solid phase at solid phase with composition E. Similarly, G is the composition of the liquid phase that is in equilibrium with the solid phase with composition H. Right here, G and H is a tie line. So you have a tie line GH, and then you have a tie line EF. So EF, the two endpoints, are the equilibrium compositions of the liquid and the solid phases, and this tie line basically is the equilibrium of the solid phase, and this is equilibrium of the liquid phase. Right now, if you look at that, if you see that these are both regular solutions with unequal enthalpies of mixing. So if you see unequal enthalpies of mixing means your regular solution models will be different, slightly different, right? They will have different shapes. For example, the solid curve has a different curvature than the liquid curve, right? The liquid curve that you have has a different curvature than the solid curve, right? So one is slightly less spread, another is more spread, but a liquid, for example, has slightly more depth in the middle, and solid has slightly less depth in the middle. It is slightly less shallow. It is more shallow. solid free energy curve looks more shallow, and liquid free energy curve looks more deep. And but why does this happen? Why are the shapes so different? The shapes are different because the models are different, and also in these models, the enthalpies of mixing or molar enthalpies of mixing are unequal. So as a result, if you see that, you will again see that once we do this, so you have this solid curve here, right? You have this solid curve here. So if you look at the solid curve, you have this solid curve here, and you have the liquid curve here, and then you have this tangents, right? So the liquid curve is given in pink, the solid curve is given in yellow, and as you can see, solid curve is more shallow than liquid, right? At the equiatomic composition, or at or near the equiatomic composition, and also they have different curvatures. So as a result, if you see the tangent construction here, you will see that you get into this G and H here. And if you do the tangent construction here, you can see this blue curve, right? You can see this blue curve, this blue line that we have. So, right, so this is the blue line, and this is another tangent that we have. And so from these tangents, you can basically tell that this tangent basically gives me this is going to be my composition of the liquid phase in equilibrium with the composition with solid phase, denoted by E, right? So this is the composition of the liquid phase denoted by F, right? This is F, and this is the composition that is. So again, it comes from, you can see E and F basically gives you the points where the common tangent touches the yellow and the pink curve. The pink curve is the free energy of the liquid, and the yellow curve is that of the solid. And again, you have on the other side, you have again this blue curve, this blue line, which is a common tangent line. This blue line is a common tangent line, and it intersects, or it touches, it cannot intersect, right? It touches the liquid curve here at G, and the solid curve here at H, right? So it touches it at H. So if I look at this, just complete it, right? So I think the G is like this place. Done. So now we have to also understand another very important point, that is the liquid and solid states, right? You have this liquid free energies and solid free energies. In all these free energies, we always use some standard state. Now, if you see the case here, Tm of A is greater than Tm of A is less than Tm of B. That's the melting point of A. So in this diagram, very quickly, is less than Tm of B. Now I am looking at a temperature T, say this temperature. Now we have this liquid plus solid equilibrium, and we have these two free energies. Now if you look at this very carefully, this is the liquid free energy. See, this is this curve extending from here, goes up to here, is the liquid free energy, and this curve extending from here up to here is the solid free energy. In fact, if you want, I can basically replace the solid free energy with the so pink is basically the solid one, and the pink is basically the solid one, and yellow is basically the liquid one. Now if you see that, you have 2 points here, that is, this you are drawing at some temperature T, right? This is what you are drawing at some temperature T, right? Now at this temperature, if you look at that, at this temperature is above TMA, right? This temperature is above TMA. That means at this temperature, the pure A should be liquid, right? So at this temperature, pure A, the liquid pure A free energy is here, because here you have basically a liquid phase, right? So basically at this temperature T, the liquid phase free energy is less than the solid phase free energy for pure A, right? For pure A solid, the free energy is more than pure A liquid at this temperature, right? So basically, solid to liquid, if you look at, solid to liquid, if you look at, so this is like a melting condition. Solid has a higher free energy and liquid has a lower free energy. So solid to liquid means GA0 liquid minus GA0 solid, but GA0 liquid is already less than G0 solid, that is it has to be negative. So delta GM A solid to liquid is basically G0 liquid minus G0 solid, which is basically negative. So basically that's what I have written, right? So this is more than this guy, or this is less. The GA0 liquid is less, right? GA0 liquid is less than G0 solid. As a result, this guy has to be negative, right? Now, if you look at B, TMB, that is the melting point of B is higher. So basically, it's solid here will have a lower free energy. The solid here will have a lower free energy. So solid has a lower free energy here, and the liquid has a higher free energy here. So basically, if you consistently look at this delta G0M, that is the molar free energy for pure B, right? 0 and B basically tells you it's for pure B. Then delta G0B from solid to liquid is basically, again, solid to liquid, right? Final minus initial. So liquid minus solid, right? G0B liquid minus G0B solid, right? G0B liquid is basically higher temperature, higher value, right? At temperature T, G0B liquid has a greater value than G0B solid. So basically G0B liquid is greater than G0B solid at temperature T. However, G0A liquid is less than G0A solid at the same temperature T, right? Because of the melting point differences, because T lies in between TMA and TMB, that is the melting points of A and B. Now, what should you choose as a standard state? You can choose anything. You can choose the reference state to be anything. It can be A in solid and B in liquid, or it can be A liquid and B solid. So it depends on or both A and B in the liquid state. That's also possible. The only thing, you have to be very, very systematic and careful when you calculate, right? Remember one thing, whatever be your reference state, your common engine construction does not change. Common engine construction remains as it is, right? Whatever be your reference state. Only your reference state, you should be consistent. Say, for example, for the liquid, if I take A in the liquid form and B in the solid form to be the standard state, then basically A in the liquid form and B in the solid form has to be taken as standard state also for the solid phase. I cannot switch standard states from phase to phase. So for the liquid phase, if I tell A liquid and pure A liquid is my standard state and pure B solid is my standard state, then for my alpha phase or for my solid phase, also I have to do exactly the same, that pure A liquid is my standard state for A and pure B solid is my standard state for B at this temperature, right? So that is exactly what I am trying to say. So basically, if I tell solid to, so this is like liquid to solid transformation. So it's like a freezing transmission. So where you have solid to liquid, G0 solid, but remember this is positive. G0 solid is greater than G0 liquid, right? Because liquid has a lower free energy, right, at this temperature. So G0 solid minus G0 liquid is minus of delta GMA solid to liquid is minus delta G0MA, right? So it is basically GL liquid, so minus of delta G0MA. By the way, minus delta G0MA is basically, so if you see this is positive, right? Positive, and this is negative, and so there should be, this guy has to be negative, right? So delta GMA itself is negative, so this becomes positive, right? Because this is greater. So as this is greater, so this has to be negative to make it positive. Now this is liquid to solid transformation. Now this you can basically tell that delta G minus delta G0MA is minus of this delta G is delta H minus T delta S. So that's what I'm writing, delta H0MA. So basically this is the molar enthalpy of mixing, molar enthalpy of pure A. So this is molar enthalpy of pure A, and this is molar entropy of pure A, right? This is molar enthalpy. So this is the molar enthalpy of mixing, or change in molar enthalpy for pure A when it transforms from liquid to solid or solid to liquid, right? So basically when I'm looking at that, so when I'm doing delta GMA solid to liquid, so basically we are looking at melting, right? We are looking at melting. So basically this is equals to minus delta H0 Ma. There is a enthalpy of, there is a change in enthalpy or change in molar enthalpy or molar enthalpy associated with this solid to liquid transformation. Again, this is the molar entropy associated with solid to liquid transformation of pure A. Solid to liquid transformation of pure A. So that's why we put a 0 here in the superscript. Now, at T equal to Tm, solid and liquid are coexisting. So at T equal to Tm, delta Gm is 0. Delta Gm is 0 has to be equal to 0 at T equal to Tm. Now, if that is so, if you now put it here, so this is 0. 0 is this minus this. So basically, if I can write delta S0m, that is the molar entropy of the pure A, the molar entropy of pure A during solid to liquid transformation, right? Molar entropy of pure A during solid to liquid transformation is basically a ratio between the molar enthalpy of pure A by the melting point of A, right? Molar enthalpy of pure A by the melting point of A, right? Now, this is your entropy because this has to be 0 at the melting temperature, right? TMA is the melting temperature. Here, TMA is the melting temperature of pure A. Now, if that is so, I am just putting it here. So, basically, delta HM is 0 minus T, delta S M is 0, and delta HM is 0 minus T, delta HM is 0 by delta T, right? From here, from this equation, you are getting that. From this equation, you are getting this one. So, if you have that, this can be made common, and you get 1 minus T by TMA, which is basically TMA minus T by T. Fantastic. So, we got the delta G0MA as TMA minus T by T. Now, if you can see here, TMA is basically less than T. So, TMA minus T is negative. So, basically, delta G0MA is negative by itself. So, this means solid to liquid. So, if it is liquid to solid transformation, then it becomes positive, right? Because again and again, liquid has lower free energy than this pure A. On the other hand, T is less than TMA. So, there the liquid has, so the solid has less free energy. So, solid has lesser free energy, while liquid has more free energy. So, basically, delta G0MB is positive, right? Because if you look at the liquid and solid, so this is liquid has a higher free energy. So, this is delta G0MB, which is positive, right? Delta G0MB is positive. Now, you have AD, which are the gives free energies of unmixed liquid and liquid A and liquid B, right? So, this is A and D are unmixed liquid A and liquid B, A and B, right? And C and B, right? A, B and C, or C and B are gives free energies of unmixed solid A and solid B. Now, standard state you can use anything, but we are using unmixed solid liquid A and unmixed solid B. Now, if that is so, now you see one very important thing here. So, minus delta GMA 0. Now, if you see when XA equal to 1, you have the difference is minus delta GMA 0. Now, I am looking at the equation of line CB. Now, if you see, if I go further down, say for example here, it will be minus delta GMA 0 times the composition, right? So, basically, at this point, so basically the composition of A, right? It will vary as composition of A. So, because composition of A varies from 100 here to 0 here, right? So, basically it is varying with the, so basically if you look at the CB line, you see the CA and you see this line distance here, this distance, this and all. So, ultimately, basically, yeah, as you can see here, the line CB, the equation is very simple, delta GMA 0, right, times XA, right, times XA, because XA is 1 here and XA becomes 0 here, right, XA is 1 here, right, here XA is 1 and here it becomes 0, right. So, this is your delta GMA 0. So, delta GMA 0 into XA, and XA is 0, XA is equal to 100, or XA equal to 1 in the when you have pure A, and it goes to 0 as you have pure B, as you move towards pure B. So, basically the equation becomes XA times minus XA times delta GMA 0. This minus is because delta GMA 0 by itself is negative, right? I am putting a minus d del, right? Minus delta GMA 0. So, basically that's what I have written. And similarly for line AD, if you look at line AD, so this is the one plus delta G0 MB. Now, if you look at the line AD, you see at dB, delta G0MB is full, right? Otherwise, it becomes smaller and smaller. So, if you look at this, if you look at this, if you look at this, the values become smaller and smaller. So, this is delta G0MB, okay, that is the for pure B, okay, liquid to solid transformation, we are writing delta G0MB. So, liquid to solid transformation, remember, or solid to liquid transformation. So, we are writing this. Now, once we have written this, it has to be multiplied with. So, basically, if I look at the AD line, it will be multiplied with XB. So, this is very, very common sense and you can understand, right? Line AD, the equation is, the line AD, the equation is this, right? And now, if you see the formation of a homogeneous liquid solution from pure liquid A and pure solid B at any composition is a two-step process. How? Because if you have liquid A and solid B, it's a two-step process. What is a two-step process? First thing is XB, because it has to become, it has to go to the liquid state, right? So the first thing is melting of XB moles of B. Now, when you multiply so delta G0MB is basically from solid to liquid transformation. Solid to liquid transformation, right? So basically, if I look at that solid to liquid transformation, which is basically, now if you see the solid to liquid transformation, please understand. So this is the solid and it goes to liquid, right? So you require to apply. So basically, you have to apply energy because liquid has a higher energy than solid, right? Because T is basically less than T of P, right? So now, if that is so, you have this term, right? So you have, where is that? This term. There is the first step, which is basically XB times delta. So XB is the molar composition of the alloy. So melting of XB moles of B, the composition of alloy is XB. So XB times delta G0MB. Now, and then mixing of this XB moles of liquid B, or XB atoms of liquid, XB moles of liquid B with XA moles of liquid A to form an ideal liquid solution, which is basically delta G ideal mix, which is RT XL XA plus XB. Now, if you have that, then you have, and you also know, so basically, now molar Gibbs free energy of formation of an ideal liquid solution is basically you just add it together, right? You add steps 1 and 2, so you have like delta G1 plus delta G2, and so this becomes XB delta G0MB. So this is the term, becomes the first term, and the second term is like this. Okay, and this is the equation of the curve marked as. This is the equation of the curve marked as. Similarly, for an ideal solid solution from liquid A and solid B, again, you have to freeze the liquid, right? You have to freeze the liquid. You have to freeze the liquid. Again, you have to minus XA delta G0MA, right? Which is basically, you are basically time plus RT XL and XA plus XB. So here, so in the case of ideal solid solution, A has to be frozen, right? So which is basically given by this expression, right? So basically, it is solid to liquid transformation. So solid to liquid. So minus of delta G MA or delta minus of delta G0 MA. So basically that's the idea. So minus of delta G0 MA. Right? Minus XA delta G0 MA plus RT XL XA plus XP and XP. Now if you look at the equilibrium, you have to see that this is like mu AS equals to mu AL and mu DS equals to mu BL. Or you can also write this, right? There is the partial molar free energy of component A in the solid state should be equal to partial molar free energy of component A in the liquid state. Similarly for B. Okay, now you have the mu A, the equation. The mu A equation is you have d delta G dx, d delta G dx, which is basically coming from here, right? Do d delta. So you already know d delta G liquid, right? D delta, this is the molar free energy of mixing for the liquid solution. This is the molar free energy of mixing for the solid solution. Now, if I know this, I also know its derivative, right? D delta G dx, I know. And we know that formula. So, the formula is delta G minus x into d delta G dx. So, basically, if I know the formula, so what is mu A liquid? Mu A liquid is this, right? Delta G liquid plus XBL times d delta G dxa. Now, if I have that, so basically dxa liquid, right? Now, if I have that, we do a little manipulation. So basically we get RTL and XAL, right? So for solid also, if I have a look at solid, and if you do that, you basically get RTL and XAS minus delta Z0N. So basically you get RTL. So if you equate them, you basically get RTL and XAL equals to RTL and XAS minus delta G0N. Right? Similarly for MUL, you have RTL and XBL plus delta G0MB. And for BS, it will be RTL and XBS. So this is equation 1, this is equation 2. Basically, if you have these two equations, you can basically get the mole fraction of A or composition of A in the liquid, right? XAL basically denotes the composition of A in liquid, which is equal to composition of A in solid times exponential minus delta GM0 by RT, right? Minus delta GM0 by RT, right? And 1 minus XL is 1 minus XX, so that is from 2 into exponential minus delta G0MB by, right? So that is the idea. So this is basically 1 minus XL is nothing but XBL, right? So you have XBL. So XBL equals to XBS exponential minus delta 0 MB by R. Now from 3 and 4, so this is your 3 and this is your 4. Basically you can write XAS and XAL. So basically so if I know this, so XAL and XAS, right? So basically XAS and XAL. So you know 3 and 4, and you know XAS, and you know XAS, and you know XAL, right? So if I want to do this, we can further simplify it. How do I simplify it? Because you have XAL and XAS, and you have two equations, right? You have this equation and you have this equation. Now if you want to eliminate, it is nothing but XAL by XAS, which is exponential minus delta, and so 1 minus XL by 1 minus XAS, which is this equation, right? So basically, if you have that, you can do a little bit of manipulation to get XAS to be 1 minus exponential minus delta G0 MB by RT into divided by exponential minus delta G0 MB by RT and minus of exponential of minus delta G M0B by RT. So basically, you get the composition of A in solid, and you also can get composition of A in liquid. Now, how do you do this manipulation? The idea is very simple. You have 1 and 2. From 1 and 2, you are basically writing XAL and XAL and XAS. So basically, if you know these two equations, there are two equations and there are two unknowns. One is XAL, another is XAS. These are the two unknowns. Now, if you have these two unknowns, XAL and 1 minus XAL, and you have XAS and 1 minus XAS, so two unknowns, two equations, you are basically doing a little bit of manipulation. So basically, you can write 1 minus XL plus XL is 1, and you have XAS exponential minus GM0 by RT, and 1 minus XAS exponential delta GMB0 by RT, and this is equals to 1. So basically, from there, you can obtain XAS and XAL. So this is just a little bit of algebraic manipulation. Now, once you have done such manipulation, now you can basically look at so what you got is basically the concentration of A, right? You have got the concentration of A. So basically, you have got XAS in terms of, so you know RT, you know this guy, and so you know with temperature how the composition of A in solid will change and A in liquid will change. So if you know that, you also know basically the B in solid and B in liquid. So basically you know the equations of the liquidus and the solidus, right? This gives me the equation of the, so this gives me the equation of the solidus. So this is the solidus line as a function of XAS versus T, right? You get XAS versus T, and this gives me the equation of the liquidus, right? So this is how you can basically explain the equations. And you see, if you have any, so one thing I wanted to tell you, that if you do this free energy composition diagrams, you can basically analyze any equilibrium. Say for example, if I have this eutectic, okay, if I have eutectic point, so basically at TE, if I just look at TE, at temperature TE, you see alpha, so basically this is this point, this tells that This is the alpha liquid and beta coexistence, but this is the composition. So this is where it comes in handy. This is the composition of liquid, this is the composition of beta, and this is the composition of alpha at the eutectic temperature. At the eutectic temperature, this is the composition of liquid, this is the composition of beta, and this is the composition of alpha. As you can see, composition of liquid is between composition of alpha and composition of beta, unlike the periodic. Right? Now, if you have that, you have the alpha free energy, you have the liquid free energy, and you have the beta free energy. All of them will follow the same common tangent at T. And this basically corresponds to this point, this basically corresponds to this point, and this composition corresponds to this point. Right? So, this is at T. Now, if you go below T, say for example at TD, you will see at TD you have only alpha and beta. So, the liquid basically just goes up. Liquid does not remain in the common tangent. So you have the alpha composition. So you have the alpha composition and the beta composition. There is no liquid because the liquid has gone up. Right? Liquid does not come in the common tangent. So basically at TD, you have only this phase and this phase, the alpha phase and beta phase. And these are your compositions. And this is exactly the compositions that you have. Right? And say for example, this is T small d. This small d is basically below T. So TD is basically less than T. And this T is greater than T. Now, in this case, what you will see, you will have alpha phase as well as the liquid phase. So basically, you see, you have alpha liquid. So this is the liquid composition. This is the liquid composition in equilibrium. So this is the liquid composition in equilibrium. This is the alpha composition in equilibrium. And you have again a pure liquid region. So this is basically, as you can see here, that after that, so after this, there is a gap, right? There is a gap. So this is the pure liquid region. And then again, you get into beta plus liquid region. So this is basically marked by these 2 points, right? These 2 points in the tangent. So these 2 points basically mark these and these 2 points. You can see this point and this point are the same as this point and this point, and you basically get the liquid beta equilibrium. And then finally you have, so beyond this point you have pure beta, and before this point you have pure alpha. So alpha plus liquid, right? Alpha, you have alpha plus liquid, then beta plus. So again, this gives you a coexistence beta plus liquid. So this is the region of beta plus liquid. Okay, and this is the region. So you can just do one thing. You can just extend this point. So basically, you can extend this point. Basically, you extend this. You can easily see this. So you can now mark them. You can now mark them. So this is alpha plus liquid, and this is liquid, and then this is liquid plus beta, and then beta. Okay, so basically you can see that at TE, mu A L equals to mu A alpha equals to mu A beta, or we can do it for mu B L, mu B alpha, mu B beta. So you have 4 equations, right? So if you look at, very similarly, if you look at the peritectic composition, then again you have this beta composition, you have the liquid composition, but here you see the liquid composition, see alpha, beta and liquid, all of them follow the same common tangent, right? All of them at the peritectic point, right? At this reaction should point alpha, beta and liquid, but beta composition, see here the beta composition is between alpha composition and the liquid composition, right? Alpha composition, liquid composition, beta composition. So beta composition is right. So this is exactly. So next we will discuss the criteria for phase stability in the next lecture. Yeah, 12th week lecture. We'll start with the criteria for phase stability and we'll do some numerical modeling in the first part. Okay. So thank you for paying attention to the lectures. And